Okay, good morning everybody. Welcome to motion planning. Today we are going to talk about optimization-based motion planning as continuation of last week. And so just to remind you, we are almost at the end of the class now. So we have spent some time on the foundations, search-based methods, sampling-based methods. Last week, Andreas started with the optimization. And today and a little bit of next time, we will continue with that. And then we will just have basically 1.5 weeks left for some more advanced topics. Okay, so last time you looked at optimization mostly from a geometric motion planning perspective. So one method was the post-processing of solutions that you might get out of things like RRTs that tend to be not that smooth. And one way was shortcutting, which is a gradient-free method, or you can use that initial guess and fit some splines. And you looked at different splines last time that can be fit. And then you can also alternatively directly plan using optimization. And so you considered the spline optimization using polynomials and Bezier curves. And then you also looked at one kind of concrete algorithm called CHOMP, which was operating on these signed distance fields and trying to optimize using that particular data structure for collision avoidance. Okay, and then really the big thing that is left is that we look at kinodynamic motion planning and not only geometric motion planning. And for today we have kind of two topics that achieve that. The first one is a method that allows us to use splines, also for the kinodynamic case. And the second one is called sequential convex programming, which really allows us to solve any kinodynamic problem. Okay, so let's first look at the differential flatness case. And so for that, we first need to know what it is. So the first observation is that, or the motivation is that we would like to use these sort of splines also for the kinodynamic case. And the reason is that they're already kind of smooth and they also have this temporal component. If you remember, these polynomials had this t. The t was between 0 and 1 and can be seen as a time if you want to. And so in order to achieve that, we have to look at what a differentially flat system is. And so I have the abstract definition, and we look at it in a second on a concrete example. So if we remember, the kinodynamic case is defined by having this dynamics function, which tells us how does our state change given our current state and our action. And then we call that particular system differentially flat if we, in this outputs set of t, if we can find two functions like this gq and the gu that compute the q of t just given this latent variable absolute, the first derivative, second derivative, and so on. And we need both functions. So we also need another function that kind of maps this latent variable to our actions. So in other words, if we have a sequence of these latent variables and also a way of computing the derivatives, we could directly compute both the state sequence and the action sequence, which is the output of a kinodynamic motion planner. Okay, so that's maybe a little bit abstract. So let's also look at a more concrete example here. So if you recall, we looked at the unicycle I think maybe in one of the exercises before. But the unicycle is like a very basic first order model where your state space is the position, x and y in 2D. And then we also have theta, which is the orientation in that 2D plane. And you can control it by directly changing the speed or by directly changing the angular velocity, which is similar to the speed. And then the dynamics function q dot is defined by these equations. So it's basically the speed times the cosine of theta, speed times sine of theta, and then theta dot is already the other angular velocity. Okay, and so this model is like, people like using it because a lot of robots approximate that. Like maybe the most famous one would be like your vacuum cleaning robot is a differential drive, but it's possible to map a differential drive to this like unicycle model. Okay, and now, so I just copied here again the dynamics. It's the same from the previous slide. And then that's like a little bit magic in these differential flat systems, but you have to pick something for this latent space Z. And so here I will just propose that we just use the position. So it's slightly less than what the original state space was, where we also had the orientation. And now what we're looking for is these sort of mappings or functions that I proposed earlier. So let's go through these transformations. So again, here are the dynamics. And so in the first step, what we can do is that we just divide this first equation by the second equation. So we get y dot over x dot equals s times sine theta over s times cosine theta. Now, if we assume that s is not 0, these kind of cancel out, and I can simplify the sine over cosine to just the tangent. Okay, and then I'm interested in this case what theta is. So I take the arctangents on both sides. Then on the right-hand side, I have theta left. And on the left-hand side, now swapped, I have just the arctangent of y dot over x dot. So far, so clear, I hope. Okay. Then this one is a little bit more involved. So let's now say we are interested in figuring out what S is. So this equation kind of told us, okay, if we just have y dot and x dot available, we can directly recover theta. Right? But the other thing that we don't have from the dynamics equation is S. And so what we do is we just pick one of these equations, like for example this first one that we have, and change it so that we get S on the right-hand side. And that would be just S equals x dot over cosine theta. Okay, but since theta is not really part of our like latent space anymore, so we use the results that we came up with from earlier, and we really just replace the theta with this result, and then we get this sort of longish equation. Then the next step is maybe less straightforward, at least kind of for someone like me who's rusty on it, but there's like a transformation of cosine and arctangents that basically gives you this result. And if you don't know how to get it, you can just use like Wolfram Alpha or any of these tools, right? So these are basic transformations. And then you can simplify it a little bit. So the 1 you can replace by x dot square over x dot square. And then you take it out of the square root over here. So then the x dot at the beginning kind of cancels out, and you get this nice equation over here. Is that equation surprising? No, right? So it's kind of logical that the speed is really just the velocity, like the kind of cardinality of the velocity vector, right? But maybe it's important that you also see that you can derive it. What is important here is that if we think of the vehicle being able to moving forwards and backwards and would like to have a positive or negative sign, then that we can't easily recover here, right? So that's why we have the plus minus at the beginning. Okay, and then the other thing that is kind of left is to figure out what that omega is, the angular velocity. And so by definition of dynamics, it's theta dot. Theta we also just found at the very beginning is this arctangents of y dot over x dot. And then again, that's something you can kind of look up or ask Wolfram alpha what the derivative is, and you get an expression here. And what's interesting maybe is that it's really only dependent now on the velocity and the acceleration. Okay, any questions about these transformations of things? No? Good. And then just to like summarize what we have found, we really have kind of found everything now. So if we want to compute the state just on our latent space of which was x and y and derivatives thereof, which would be x dot, y dot, x double dot, y double dot, then of course x and y we already have in the state space, and then the theta was just that what we just derived. And for u, that was basically the speed and the omega. So the speed we computed over here, and the omega we also computed over here. And in both cases, it just depends on that latent variable z and derivatives thereof. Okay, so that's fun, but why exactly does it help us now? Question for you. Yep.
I mean, we can just do geometric planning, and then afterwards we can check maybe between 2 points or more if this is feasible through this output, like if this three-dimensional output something. And like in this case, it will always output something because it's always defined. So we can reduce it to a geometric problem and then just compute our actions afterwards.
Okay, and then the geometric problem would be computed on what exactly in this example? Yeah?
On the flat output.
And does the flat output have any other advantage over? Yeah? Yeah, so that's kind of nice. Any other benefit over the original state space?
As one state component does.
Yeah, so in this case at least it's smaller, and most of the time it will be smaller. So we really just have to now plan in our latent space, as long as we find some smooth curve, for example with splines, we can then afterwards apply these two functions and really get the outputs that we wanted. And then we also said that it's kind of nice that if it's lower dimensional, then we simplify the problem. And it may seem like it's like somewhat special case, but it turns out that a lot of mobile robots have these nice properties. So we just saw it for the unicycle, like omnidirectional robots, differential drive robots have the same. Car is the same thing, especially also if you pull a trailer, which I always find maybe unintuitive. But then the flat output space is really just the position of the car that pulls the trailer. So you can really just plan in that XY space. And even if you then have 10 trailers that all kind of have like an angle and so on attached to the car, that flat output is sufficient. So that's kind of cool. And then also multirotors is quite interesting because the nominal dynamics of multirotors are at least 12-dimensional. And with the differential flatness, you can plan in a 3-dimensional state space. So that's already a factor of 4 reduction for your planning, which I feel is quite significant. So people like using differential flatness in practice. And because of that, both in motion planning and also in the controls community. Okay, and here's like one concrete case study. So if you think about a multirotor, what basically happens, these 12 dimensions are the position, which is typically 3-dimensional. Then the orientation, which depends on your encoding. Like if you use Euler angles, then it's also 3-dimensional, but you have some problems. You can use a rotation matrix, then the orientation would be 9-dimensional. Or you can use quaternions, then it becomes 4-dimensional with some constraints. Then the velocity, it's another 3-dimensional vector. Angular velocity, it's 3-dimensional vector. So depending on which encoding you use, it's between 12 and I guess almost 20 dimensions. Action space is typically just speed on how you rotate each of the propellers. So it's 4-dimensional if you have 4 propellers, or 6-dimensional if you have more. And then the flat output is typically just the position. Technically, you can only use the yaw angle, but because it's kind of an optional degree of freedom in these flying robots, people often even set it to 0, and it works fine. And then you can achieve shockingly aggressive maneuvers with this. And so I just wanted to also show a little video. So that, I think, is work from maybe 2012 or so. So it's super old, right? Like over a decade. But just by planning in these flat output spaces, you can get reference trajectories like that. And I think that's quite cool. Also in the programming assignment, you will work a little bit with optimizing splines, and you will see how fast it is, like for an optimization algorithm to find solutions. Much faster compared to, like, let's say, RT or the other methods we have looked at. Okay. Then, of course, there are some challenges in practice. One we have seen in the video where the quadrotor actually moved through that window, and you could see that surroundings of the window as an obstacle. So how could we handle obstacles in this differential flatness case, based on your knowledge from last week? Yeah?
If we only have the yaw angle, then it means that in the flat output we can plan with the orientation, with the full orientation. But maybe we could, if we test, can we get to that state in geometric planning? We can basically compute this flat output to motion path transformation, and on that motion path we can compute the collision.
So that's absolutely correct. So we can definitely use this first function we had, get out the full state space, and then do collision checking. But then if our collision checker says, okay, there's a collision, what do you do then? Give up. Okay, what did you do last week for geometric planning and collision avoidance?
We will use some distance field, and maybe we can do that here too.
Interesting. That was in a slightly different context. I think the sign distance field was when you like directly optimize these points or whatever. But you also looked at maybe one or two methods for collision avoidance when you optimize splines or polynomials. Okay. Then I will just remind you. I hope you did discuss it. But one idea was that you add additional waypoints. So there was this one work that did kind of this checking. And then when there was a collision, then like you first did the geometric plan, let's say with RTs, and you tried to connect it with splines. And then if you detect that after the connection with splines there's a collision, you just add another intermediate waypoint that you know from the RT is collision free and repeat. So that was kind of this very one basic version. And the other idea was these Bézier curves, which had this nice property called the convex hull property. And in the convex hull property, we would just constrain each spline into the free space, and then it's guaranteed that the smooth curve itself will also lay in the free space. Right? And so here you can do the same as long as your flat output kind of contains the position, which for mobile robot will almost always be the case. There will be the position plus something else. But if it doesn't, then of course your decision variables wouldn't be part of what you can constrain. Okay, and then we also typically have dynamic constraints, right? So dynamic constraint could, for example, be that our unicycle has a limited speed. Let's say we can only go 2 meters per second. Now here, this is not really guaranteed. So do you have any idea how we could constrain that? Okay, good, because that's not really straightforward. And we will discuss it now. So definitely, like, it's unclear, just given this flat output space, how we could constrain S. And one method that is mostly done is this temporal scaling, which I want to discuss in a little bit more detail now. And in principle, it works on kind of all sorts of splines, but I will just discuss it on the polynomial because then it can be very concrete. So if you remember that polynomial had this form, so we define it by these n plus 1 kind of scalar values, and then the equation would be it's a0 plus a1 times t plus a2 times t square plus a3 times t cube, and so on. And that t was always forced to be between 0 and 1 in this case. And so the question now is, can we also scale it to some other value? And one idea would be to just normalize it. So if we instead have some arbitrary time horizon uppercase t, and that our t can now be in it, then we can try to transform it. And so we get this p tilde, and then we just replace that original t we had before by the t over uppercase t. And so you can see this term again If the previous t is between 0 and 1, the new t is between 0 and t, because we normalize by t, we again get in this bracket some value that's between 0 and 1. Okay, then we have this power of k, so we can just put it on both terms, t to the power of k, uppercase t to the power of k, rearrange a little bit, we get this. And then we can just rename this ak over t to the power of k to be this ak tilde. And then it looks exactly like this. So what we have achieved is that it's still a polynomial that follows this sort of definition, but our constants that defines a polynomial have changed a little bit by a pretty simple conversion, just dividing by some numbers. Okay, and then once you do that, you can also compute then, of course, derivatives, which would be for the cubic spline. That is like the regular derivative you studied last week. And then if we just write it out again with respect to the original things, we kind of get this. So, not really magic. Now, if we assume that, we look at it more at a vector perspective, right? And P really at the end describe x, y positions, then this derivative is our x dot and y dot. So in some sense, it describes the speed. So what actually happens to the speed here if I increase our time t? Yeah.
Well, it gets slower. So if I get double the time, or get half the speed.
Yes, I'm not sure about this calculation exactly, but because you also have these funny squares and cubes and so on, but it definitely will get slower.
Yeah, but like these squares, cubes, I think they will cancel out because there you also have t squared and t cubed and etc.
Yes, and I think what's kind of also important intuitively is what we essentially do here is that we say, instead of traversing that motion in 1 second, let's say we traverse it in 10 seconds. And then, of course, we expect that the velocity will go down, right? But also mathematically, what really happens is if t goes to infinity, then the speed really goes to 0, right? And maybe also intuitively that's kind of clear. Okay, and then the whole idea of temporal scaling is that we first solve our problem in the flat output space with any arbitrary kind of time, like we don't care. Then we estimate what our constraints might be with the current solution. So the constraints here could be the speed, could also be the angular velocity. If that is kind of too large, so we are moving too fast, then we just decrease. If we are too slow, which can happen in an airplane, for example, then we decrease. Wait, now I'm really messing with the signs. So if the lower bound is bigger than the maximum magnitude, so we are too slow, then we just decrease that temporal scaling, right? So we essentially make it faster. Otherwise, if we are too fast, then we increase our temporal scaling. And then if we are fine, so we are within our bounds, then we can just return. Otherwise, we update our coefficients, and that's why I kind of showed you that this update is pretty easy, right? It's really just if we have polynomials dividing a few numbers and get a new solution, and we kind of repeat. Okay, and now one problem is really what does decrease and increase mean? That's typically some sort of hyperparameter. So you either like multiply with some sort of factor, or you add or subtract, depending on how you feel about it. Another way could be some sort of binary search instead. So instead of having this loop, you just have a whole range of things that you want to try, and then you very quickly come down to a solution. Then rescaling, or this update coefficients down here, is extremely fast. What is not so fast is computing this function. So that's typically done numerically. Like in practice, it really means for polynomials, for example, you would compute the derivative of your polynomials and you sample it at different points, and you actually compute the magnitude. So not so great. And there are approximative methods for this, but they are not like accurate, right? They're just giving you some bounds. So most people really do the sampling. Can you think about any sort of problems with this?
Yeah, so this is guaranteed to every time, right? So if we have, if we always run into some derivative magnitude which is out of bounds, like this will not return.
And can one of you come up with a concrete example where this might happen? Yeah.
I think maybe like an airplane. So somewhere where you have at some point in the path a lower constraint that you hit, and on the other part of the path a upper constraint that you hit. And if you try to scale up the path, you hit the one bound, and if you scale the time down, you hit the upper bound again.
Exactly. So if you only have one of these two bounds, it's typically not a problem, mostly because we have seen that we can slow it down arbitrarily to almost stand still by increasing the time horizon to infinity. But if you have both bounds, it's really not guaranteed that we find something. Another challenge is that our optimization might not really optimize our actual objective, right? So typically when we do these spline optimizations, we use as objective, for example, the integral of something. So like minimize the acceleration of our vehicle. But if we are after something like time optimality, so really minimizing the time to go to the goal, that is a different objective that another motion planner, like optimizing RT, for example, would come up with different solutions. Okay. So how do we use it now in practice? So the approach, if you see a new robot dynamics, is first that you need to verify that your robot is somehow differentially flat, ideally in the workspace, because otherwise we can't add these constraints. Then we optimize in our workspace using either polynomial splines or Bezier curves. Then we check for the limits, and we do this temporal scaling. Usually that's also this iterative process. And then finally we use these sort of functions that we defined at the beginning from the differential flatness property to really output the result we are interested in, which is kind of the state sequence and action sequence for our vehicle dynamics. Okay, and then the optimization itself is typically looking something like that. So we want to find this sort of sequence of our latent space variables. We often optimize something like the acceleration. If we do Bezier curves, we make sure that our control points that we optimize for on a safe convex region. And then we have a number of constraints. Like the first one is that we actually really start at the beginning, that we end at the end, and then we want to make sure that there's no weird jumps between the different segments. So here, that's a jump in position between the first and the second segment, jump in velocity, jump in acceleration, and so on. Why do I say it that detailed? Because there's a programming assignment coming up where you exactly have to implement that. So if you have any questions, let me know. Everybody clear on what the decision variables are? Yes?
Like in the last step where we did like this temporal scaling.
Yeah.
The temporal scaling is always on the whole path, right?
That's one problem, because if you just scale one of these segments, then you would violate these constraints here, right? Like this one is still fine, but this one will be violated. And that's also like a big problem if you plan for very long horizons, because then you're more likely to hit this issue, right? Like if for very short motions, it's not an issue, but if you plan for an airplane for an hour, it's much more likely you will not find the right thing. Any other questions so far? Okay, then we can move to the next topic, which is sequential convex programming. And that method is more generic in the sense that we can apply it even to systems that are either not differentially flat, or where we don't know if they're differentially flat, or where maybe our objective is such that the differential flatness is not good enough for us. Let's say time optimality. Okay, so as motivation, let's look at a fairly simple case, the double integrator in 2D, which I think you have also seen before. So there the state space is really just the position, x and y, and then the velocity, like x dot and y dot. And the action space is the acceleration, also separated by x and y. And then the dynamics are particular nice because kind of the change of x dot is really just already part of the state space, so Vx. Y dot is also already part of the state space, so you copy that. And then like x double dot is just part of the action space, and so on. So it's a nice linear system. And then if you recall, our kinodynamic motion planning problem from, I guess, lecture 1 had the following form. We want to find the sequence of actions, the sequence of states, and also the time horizon to get to the goal. We minimize some sort of cost function. We have the start constraint, the goal constraint. We want to be collision-free, and we want to fulfill our dynamics. And so this one was super generic, right? Because it kind of handles u and q as some sort of functions of t. But then in practice, we typically can't really do that unless we do the spline optimization where we get real functions. But we often also just like to discretize it. So instead of getting this kind of concrete function models like splines, we just have sequences of states. So what we could do in discrete time optimization is our decision variables now become just a sequence of t u's and t plus 1 q's. Then because we already have u in here, we could directly minimize this sort of acceleration in this case. Start and goal, quite simple. Then the constraints, let's say we don't really have an obstacle here, but we're kind of constrained in some sort of environment. So we get these environment constraints and also the velocity limits with that. And then for the dynamics, we just could use a basic Euler integration. So we just say our next state must be the previous state plus this f function, which is basically x dot or q dot times dt. And then we can also constrain kind of our u's. And so if we look at it, then we have a quadratic cost here. So quadratic, always we look at what are our decision variables, right? So decision variables are u and q. So it's quadratic in our decision variable u. But then all the constraints are kind of linear, right? So we have an equality constraint here, inequality constraint. This f is this really kind of nice one that doesn't have any funny trigonometric functions or anything. So it's also linear. dt is just a constant typically. And the other limits are also linear. So that's just a quadratic program. Okay, is that difficult to solve? Maybe? Split it up. Is it conceptually difficult to solve? Definitely not. Is it difficult for you to like take a few minutes and implement it? I see a lot of nods, so that seems difficult. So let's test that. It shouldn't be difficult. Perfect. So it's the same slide on the side, and I will upload the script afterwards, right? So you don't have to like type anything or whatever. And now I'm sitting, not ideal, but let's see how it goes. And so there's this great package called CVXPy, which is for convex optimization. And that's also the one you will be using in the next programming assignment, and that's why I just wanted to show you how it can be used. And it's kind of similar interface with NumPy. So you just import it at the beginning, and then we need to define what we're interested in. And for this, let's just look at a simple example where we have 20 time steps. Let's say our dt is 0.1. And then we need to define our q start, which I guess we do something very traditional. Then the q goal, we just kind of move maybe in a cube or something. So 1, 0, but we also end up with 0 velocity at the end. Oops. Okay. And then now the magic starts, so we need to define some optimization variables. So we have here 2, so we have the u variable, and that's basically a whole vector, and similar to NumPy, you can say how big it is. So here we have in total t, from 0 to t minus 1 is t in total. And then u itself is two-dimensional because it's the acceleration in x and acceleration in y. And then we also have q as optimization variables. And that one is now t plus 1 and four-dimensional. Okay, so now we kind of did like the left part of the optimization, the stuff under argmin. So we move our way forward and we define the cost. So the cost is just the sum of squares, which we are very lucky we already have of u. And then we can define our problem. And the problem gets kind of two arguments. Like the first one tells us the objective, and we basically wanted to minimize our cost. And then the second one is a list of constraints. So let's make it look nice and really get a list out here. And then we just have to figure out what constraints do we have. So the first constraint is that our Q0 should be the same as the start. Then the next one is that the final one should be the same as Q goal. Then we have our limits in U, which I guess I don't constrain here in this example. And then we have our constraints for all of the dynamics, which are the more interesting ones. And in the definition on the right-hand side, you see that we have quite many constraints there, right? So we have basically in total t constraints, because for every time step we have to do it. Now I don't really want to write t constraints down here, but it's a list, so I can try to generate another list, and then lists can also be added together. So this constraint would be just that k plus 1 equals qk, and then we have plus our f function, which gets qk and then uk. Then we need to multiply it by dt. And we do it in this range, right? And then we have two constrained lists, so we can add them and should get multiple lists. Now what's missing here is our function f, but we can also just define that. So our function f gets q and u as an input, and then according to our linear dynamics, we just take some parts from q and some parts from u, like this. Okay, so now we have defined a problem, and what we can do is we can solve it, and then we could, for example, look at q, and we could also look at u. Okay, so now I get, of course, some fun errors. Oh, I forgot an in, I guess.
think you have to return something in the f function?
That would be best, yeah. And what should I return? Magic. Okay, it printed something. And that's cool, but maybe we also want to see it. So what do we want to see? Maybe just how we move or like the x value or something. Actually, it would be more fun to do something like this. Yeah, it looks great, just not for you. There it is. Shocking, right? So that's maybe a little bit boring, but we really move from 0, 0 to 0, 1. And now we could change the optimization as the printing a bit. So maybe it's more interesting to look at the velocity profile that we get. Just access. Which also makes sense. So in kind of one direction we don't do anything, and in the other direction the velocity just increases. Okay. How long did it take? Maybe like 5 to 10 minutes. If you have the right library. Any questions about CVXPy? No? Okay, so CVXPy is nice because it allows you to really doesn't want to switch. Here we go. It allows you to pretty much write down like that mathematical definition in code, and then it solves it for you. And as the name suggests, it can solve all convex problems for you, which is quite nice. And if it's not convex, it will also tell you. So you can write it down, and then it tells you why it's not convex, which is great because that's sometimes also not so easy. And what it does internally, it just converts it to some solver. And you can pick also the backend. So you can use it with many different solvers, open source ones and commercial ones, depending on what you like. Okay. So now this example was maybe somewhat contrived because we had this double integrator where our f function was so simple that everything was linear and we got a QP. But now if we would even go to the next best thing, and let's say we use car dynamics, where we have these trigonometric functions, then the dynamics constraint is not convex, right? So if you remember, we did this Euler integration here. If we put in that f function, we suddenly have the cosine and sine of theta and also a tangent of one of our control inputs, which is not so good, right? Especially if, because theta would be now as part of Q, that would be part of our state space, and also S and phi would be part of our state space. And so once it's not convex, we can either use nonlinear optimization, but that usually doesn't work so well because you need a very good initial guess. Or we can try to still use convex optimization. And in order to do that, we can just linearize the dynamics. So if we have some initial guess on where's the solution y lie, which here is just called Q bar and U bar up here, then like the standard way of linearizing is to use the first order Taylor approximation that you should have heard maybe a long time ago. By definition, the approximation means you take the function value at kind of these initial guesses, and then you add these two terms or multiple terms depending on how many input variables you have. So here we have two, Q and U. So you first have the partial derivative of f with respect to Q, and then evaluate it at these concrete kind of values. So this whole thing really just becomes essentially a matrix that is fixed. And then you multiply it by Q, which is the input variable, minus the Q bar, which again is this fixed initial guess. So now it's like really just a matrix times some variable minus something fixed, which is linear. And then the second term, same thing, partial derivative, but now with respect to U. Okay, so to make it a little bit more concrete, in the car dynamics, we had these dynamics down here. The partial derivative with respect to Q just becomes a 3 by 3 matrix because we now compute the derivative with respect to each of the state inputs. So this dynamic does not depend on x and y. That's why you get zeros over here. This last one doesn't depend on theta. That's why you get a 0 here. And then you get some values because a derivative with respect to theta is this one and that one, right? And with U, the same thing. It's now a 3 by 2 because you compute the partial derivatives with respect to the two action spaces S and phi. And you get this matrix. And then this notation again meant that we evaluated at our concrete points. So now we would put in concrete values for S and theta, and we really just get a constant matrix. Okay, that's clear for everyone? Good. Okay, and then the basic sequential convex programming is quite straightforward. So we have some magic function that gives us an initial guess. Then we linearize our dynamics around this initial guess. Then we can construct a convex problem and solve it. And the solution gives us a new initial guess. And then we repeat. And there's some kind of convergence criteria. One is you somehow check if it's valid or not with respect to the nonlinear dynamics. Other ones would be really just looking at changes between iterations. And in SCP, it's guaranteed that it will converge to something. So it doesn't oscillate or anything, right? So if you just look at the change of x bar and u bar between iterations, at some point there will be almost no change anymore. And so there's still some challenges with this version. So one challenge is that these dynamics are kind of linearized, and that means this linearization is typically only valid around some point, right? Especially if you have trigonometric functions, that linearization is only correct if the angles don't change too much. And in order to let the solver not go crazy, we typically also constrain our solution to just make small steps by saying we cannot go too far from this Q bar and U bar. And these constraints are typically called trust region constraints, and it refers to how much do we trust our linearization to be correct. And then the second challenge is that it's a convex problem, right? So it has these equality and inequality constraints, and it's not guaranteed that there's a solution. And even worse is, even if the original nonlinear problem has a solution, after we linearize, we might have kind of pruned away the actual solution, and there's no solution anymore. Which means that in this main loop over here, solve might not return anything, and then we don't really know what to do next. And so there's kind of many different variants of sequential convex programming that try to address both of these issues or challenges. And so one is shown here, so we can see kind of the same thing. We initialize somehow, then we linearize, then we handle kind of these issues, we discretize, solves the convex subproblem, updates the trust region, and repeat. And the way they often handle these issues is that, for example, there's some slack variables. So for the second one, instead of really having equality and inequality constraints, we add some slack variables as part of the decision variables and try to minimize them. Okay, and then really implementing this is actually not so hard, at least in the basic version, because it's just the code we have just written, plus something that does the linearization. And linearizing stuff is not that difficult if you model things, for example, in PyTorch. Then you have automatic differentiation, and you can also compute these matrices automatically. So it's actually just a few more lines of code to change what I've showed you in the lecture to support the nonlinear case for this very basic version. Okay, what can you do with this? You don't have to necessarily program it yourself. There's some interesting toolbox that did it already with many different variants of sequential convex programming. And they have this fun little demo of from our aerospace, basically, where you have a rocket that somehow needs to land. And that's obviously very highly non-linear because you have all of these angles, even in 2D, and you don't have that much control. Typically you just have this sort of thrust and then something for the orientation. And you want to land at a particular spot. And I just also wanted to briefly show you that. So here's this tutorial. You see the tutorial itself hasn't been that active recently, but then the toolbox itself has some more recent changes also. It is written in Julia, which makes it a bit harder to use if you don't know Julia. But they have these cool examples, and I will just, it's also written almost like a class project. So you can see what you have to do, which is quite elaborate. And then I just wanted to show you this kind of cool demo at the end of a trajectory that is just computed. And defining these problems is a little bit annoying because you typically have to define the dynamics, and then I think in this case you also manually give it the Jacobian and so on. That's why you have to implement more things. But then once you define it and give it to a solver, finding the solution is typically fairly quick, which is good. Okay. Maybe some practical tips as well. So I already mentioned it. I don't really like computing Jacobians myself because I always make mistakes, and there are a lot of good toolboxes out there. So if you really need an analytical expression for some reason, then I would go with SymPy first. There's also Wolfram Alpha and Mathematica, but it's a bit harder with these two to deal with matrices. SymPy can naturally also handle like matrix operations. And if you don't really care about it analytically, like in sequential convex programming, technically you really just need a numeric expression at some point. Then you really can just use PyTorch or also Ajax, which has a pretty good automatic differentiation module and is a replacement of NumPy. So you just import it like NumPy, and then you get additional functions that give you basically the Jacobian at some point. Okay, and so I would recommend, like, if you ever have to do it, just use these things. Okay, then, so that's great, it kind of works well. Does it give us a global optimum? So if you recall from last time, convex optimization is globally optimal.
I think because we already discussed that maybe actually a feasible solution could maybe improve the way. I think that alone is enough to say that if there's a global minimum and we can't find it at all, and we already don't converge. And I think it's also the case if we find another solution. But maybe we don't actually find optimal.
Cool, and you even already commented on completeness now, basically. So it's not complete, and it's also not really globally optimal. And the reason is also this, like what you said with the pruning, but also the initial guess. So even so, every iteration you globally find for this convex subproblem the minimum, because the way you created these subproblems, you already removed parts of the solution space and constrained yourself. Also based on the initial guess, you do not find the global minimum. And that's maybe also kind of the primary weakness, I would say, of this method in general, is that it's highly dependent on this initial guess. And so there's many papers that kind of claim, oh, it's like easy because I can just use a straight line and it just works. But it really depends on your environment setting. So if you have a motion planning problem that is, let's say, almost forest-like, so you just have some obstacles scattered, and you initialize with a straight line, but every time to kind of avoid the trees, you just have to go a little bit left and then a little bit right. Then of course you just locally change your initial guess. But you have a maze-like environment, like some of the examples we have seen with RT, where you kind of really have to find the shortest way, maybe also through a narrow passage. Then SCP will only be able to find a solution if the initial guess is already roughly correct, right? And so that's maybe a problem because it kind of solves some part of the motion planning problem, but you usually need to combine it with another motion planner that we have learned about to computes this initial guess. Okay, now we kind of looked at some very basic things, and we also looked at, for splines, how we can handle obstacles. But for SCP, we haven't really considered how we can handle obstacles here. And that is not that straightforward. And so we have to look at it in a bit more detail. So let's look at the example over here, where we have a robot. Let's say that's A, and B is an obstacle. Then what we can do is we can try to find these closest points on just the surface of these two objects. And then this vector that connects these 2 points will have a certain length, right? And if we say if that length is positive, then they're definitely not colliding, and the length kind of tells us how close they are. If it's 0, they're touching at 1 point at the surface. And if it's negative, they are essentially overlapping. And also this number tells us a little bit how badly we are overlapping. Okay, and so these 2 points here, PA and PB, are also known as these kind of contact points, just because if it would be 0, those are the 2 points that would be 0. And this length we call the signed distance, like we discussed already last time. Okay, and then this flexible collision libraries that you learned about already can actually compute these 3 things fairly easily. So if you create this distance request, you just have to enable 1 flag. And then in this output object that you have, there will be fields filled with the values. And by default it's false, just because it takes a little bit more time to also compute that over just binary, as a binary check if there's a collision or not. Okay. Then what we can do is that we can define this contact normal called n. And if it's positive, we just say it's PA minus PB over kind of the norm. So the normal is the unit length vector. And if it's negative, then we just kind of swap the sign here. And the reason why we do that is that we can then have this equality down here. So that SD equals n dot product with this vector. Okay. And now once we have this fun equation, we can make a little bit more explicit what is happening when the robot moves, right? So then that sign distance obviously somehow depends on our configuration. So does the normal by our definition, because it depended on kind of the position of the obstacle, but also the position of the robot. And then what's happening on the obstacle is kind of the only thing that is static. Okay, and then there's like this typically the strong assumption made that actually n stays static and this PB are static. PB is less critical as long as you assume that you don't have dynamic obstacles. It can be critical if you move kind of a lot, then maybe that contact point will really change, right? So if you go back to this example over here, PB is now this corner point, but if robot A moves over here, then this corner point would be instead the different one. So it definitely, technically also depends on the position of the robot, but if the robot moves just in a local neighborhood, then maybe PB doesn't change that much. Okay. So these assumptions are typically made, and it's kind of weird that they are made, but it will simplify the math that we look at in a second. So now let's assume we have again this initial guess on where our robot currently is. And with these two assumptions, we can basically linearize our function. And we use the same method, the first order Taylor expansion. Now it's a bit simpler because we just have one variable, so it becomes the signed distance at the point we are looking at, which is this thing that comes from FCL, basically, plus the partial derivative of that SD function with respect to Q at this initial point. And then we kind of look at that function and we use our two assumptions, and because we assume n is static, we can pull it out. And so what remains is this PA, and so we need this partial derivative of PA with respect to Q, and the rest is just kind of copied again. And so now, of course, the challenge is maybe how can we compute this partial derivative, but let's take that aside first and see how it would work in practice. So let's take this example where we have a robot at coordinates 1 and 2, and our obstacle at coordinates 3 and 1. And then they both have a fixed radius, which is here, I guess, 0.5 meter, right? And they're just circular shape. Then, just geometrically, we can see that the kind of two contact points are at the surface of these two. And then we can estimate what they are, either by reading it in this figure or by just computing the points, knowing that it will be on this line connecting the centers of the two robots. Right, and then PA is roughly here and PB is roughly here. And then the length just comes from this triangle that we have is a little bit over 1. Okay, and then this thing, these three values we get from FCL, and it will really be these kind of like just numerical values, not any equations. So once we have that, we can just compute our normal vector. And so we just go by this definition, right? So it's like PA minus PB over this norm. And we get an expression like that. It's just a vector. Okay, and then step 3 is that we use our linearization that we found. So this, again, just comes from FCL. That n we just computed with values that also came from FCL. And then we have this kind of expression still here. And this one is just Q bars, what we also got from FCL. Q is our linear function, decision variable. And so we need this partial derivative still. And so the partial derivative here essentially means how does our contact point change if our configuration changes? Or in other words, how does this local transformation change if our robot moves? And this highly depends on the shape of the robot and also on kind of the dynamics of the robots. So if we think about this robot being just a double integrator with these dynamics x, y, and x dot, y dot, then this point PA here will just kind of move exactly like the robot itself moves, right? So it can just translate, there's no weird rotation. And essentially that means that our partial derivative at the end just extracts these sort of position parts from our state Q and tells us how we change. Now if we have a car-like robot, that's not quite as straightforward, because then if we look at the transformation of PA, we get the cosine and sine and so on here. Because if we would rotate in place, then of course that point PA up here will just also change in x and y coordinates. Which means that partial derivative will still have some components based on the translation, but there will also be some components based on the rotation. And now I don't remember if you actually do it in like the next exercise or if it's just for fun, but that's something we can just try either on paper or with SymPy. Okay, and then going back to this example, what we had here, now we have this expression of the partial derivative being just this 2×4 matrix. Now we can also see much better that it's really a linear operation. We can do some fun sanity checks. So we have a 1×2, 2×4, and 4×1. So we do get a scalar value at the end, which is good. And then if we just play with some numbers, for example, if we now move that robot from 1,2 to 2,2, so it would go here, then we do expect that the sign distance reduces, but is still positive. And if we just plug in the numbers, that's true. From 1.2, it goes down to 0.3. And then if we move the other way to 0,2, so that robot moves to this point over here, then indeed the sign distance is still positive, but increases. Okay, so why is that interesting now? Because now we have a linear way of expressing our sign distance, and we can just add a constraint, making sure that it always stays positive. If it ever turns negative, then we violate. And so we add this sort of constraint for each obstacle that we have and each time step. So it's quite many constraints, but all of them are linear, and then we can use our convex solver to solve it. In principle, this only works if the obstacles are convex. So if you have non-convex obstacles, you would split them up. And how to split them up, we will also discuss in a little bit. Okay, and then maybe also some comment on time optimality. So right now, one big issue is that as decision variables, we had these sequences of states and actions, which means the number of states we kind of fixed, and we also, in our little programming example, our dt was fixed. And so one way of doing time optimal planning now is to just start with a pretty large t where we're confident we can solve it, and then linearly reduce it until the SCP becomes infeasible, and then we get the optimum. What are potential pitfalls with that approach? No idea. So quite many actually. So the airplane example still applies in this case because we just linearly reduce. I mean, it's not guaranteed that we really find one setting that will work. We now add another outer loop around SCP, so that will be pretty slow. And also just initializing it correctly, like if your initial guess doesn't work, especially in the airplane example, unclear what to do. There's some ways you can improve this, like for example, instead of linear search, you could do a binary search, but then, I mean, in principle, the same issues kind of apply. What's done more commonly is to just add delta t as a decision variable. So you fix yourself to always optimize for your 20 time steps, but you say delta t can also be reduced, therefore making it faster. The problem now is that we get a quadratic constraint, right? So in particular now, if you look at these constraint for the dynamics, we get u and q, and they're divided by this delta t, which is a decision variable, so it's quadratic. And so what do? Well, you linearize, which can be a good idea depending on this, but you just basically say, okay, that's now an additional variable. You still do your first order Taylor approximation, and you basically get an additional term in that way. And then, of course, it also means you need to add another trust region around your delta t. Okay, any questions regarding sequential convex programming? Then I just want to comment on two practical things. So one is the data structure called the octomap. That one basically allows you to take LiDAR or RGBD data as input, and you create what is known as an octree, which is a very memory efficient and lookup efficient way of getting convex obstacles, because each of these regions is really just a cube, which is convex by design, and it also means you know the exact position, just generated from raw sensor data. So a lot of the things that we discussed here and in last lecture are not as crazy as it sounds, because this can be really constructed on the fly efficiently. And yeah, it has been around also for at least a decade. It's pretty widely used, and there's some better versions that are maybe faster, but not as widespread yet. And the second one that I wanted to point out is VoxBlocks. VoxBlocks is directly for sign distance fields. So it basically allows you to take RGBD data as input, and it has this data structure that then allows you to directly query the sign distance, which is very useful for any optimization-based planning, including CHOMP, that you discussed last time, and also in principle SCP. And yeah, in the interest of time, I will skip this video and maybe just conclude what we have learned today. So we started by looking at differential flatness, and the idea of differential flatness was that if we can find the special mapping from the workspace to the configuration and action space, that we can then plan extremely efficiently just using spline optimization, even for kinodynamic systems. And in principle, if that is possible, I would highly recommend you doing that first for your robot. If it's not possible, we learned one kind of optimization-based method that encodes our kinodynamic motion planning problem more or less directly using time discretization and linearization, called sequential convex programming. And then lastly, we also kind of looked at some practical aspects on where you would get the obstacles from by using appropriate data structures that can directly operate on perception data called octomap or VoxBlocks. And so next week we will spend maybe another half an hour or 45 minutes on different encodings for optimization-based motion planning. And then we will kind of take a look back at all the different algorithms that we have discussed so far and try to figure out for given problems which algorithms should we be using. Okay, that's all from my side, and I'm happy to take any questions. All right, see you next week then.